In our first motion graph example, we're looking at a car moving in one direction, in this case up the page at a constant speed. We have a bird's eye view of our car, so it's like it's moving in one direction on a horizontal roadway. The droplets there, those black dots, are representing the position of the car, and they are dropped at every 2-second intervals. We take these dots and we basically slide them over onto a Cartesian plane, where position, symbolized by x, is on the y-axis, and time, symbolized by t, is on the x-axis. We call this a position versus time motion graph. Slide over our dots. Now we get a very particular shape or type of graph here. Notice that our very first dot that was at the very bottom, that was dropped off at time equals 0 when the car first started, is right there at the origin. 2 seconds later, or 2 seconds later on the x-axis, representing time, is when we get our next dot. And it's positioned higher up with the higher y value because that's the position of where the car was. We can notice this is a linear graph. We can remove our dots, and usually this is how we see our motion graphs. The labeled axes and then the function drawn on there. So we can tell from our very first motion graph, a car moving at a constant speed in one direction will produce a linear position versus time graph. Our next example is going to be a motion diagram and motion graph of a car speeding up. Try to imagine what the shape of this graph might be before we put the dots onto the graph. Here comes our car. It's starting out very slow at rest and then picks up speed. Initially, you can see that the droplets or dots representing the car's position are starting out very close to each other because the car is not moving very fast. And as the car picks up speed, the dots get further and further apart. This again is the car starting out from rest and speeding up. We're going to slide our dots over onto the position versus time graph. Try to imagine what the shape will be. Remember, the dots are still dropping every 2 seconds, but now we get a different shape. The dots are still equidistant on the x-axis because they are equally spaced in time every 2 seconds. But now, on the vertical axis, representing the car's position, the dots are more spaced out because the car is picking up speed. The higher the speed, the greater distance the car will travel in every 2-second interval. Now, when you draw motion graphs, and really also when I draw them, we want to do our best to draw a curve, not connect the dots, but I'm kind of limited with the program I'm using right now. An object speeding up at a constant rate will produce a squared or quadratic motion graph on the position versus time motion graph. The next example we're going to look at is going to be a motion diagram and motion graph of an object slowing down. So you're going to see in a moment the car coming up from the bottom of the page at a high speed before it starts to slow down, and it will eventually stop at the top of the page. We're going to include the car being stopped at the very end of our graph this time. Notice the car is moving at a high speed initially, so the dots are further and further apart. But as we slow down, the dots get closer and closer together because the car is covering a shorter distance in every 2-second interval as it slows down. We still have our position x as a function of time t graph, or position versus time graph. We slide our dots over, and we can see we have now a different shape. This is not linear, but it's not the same curve as last time. We have a different curve. Now we have a curve bending in the other direction. Remember, our car is moving in one direction and slowing down as time goes on, and then it stops. You'll see in a moment the first section of the graph that I highlight with a dotted red arrow is going to be the section of the graph, or the portion of time, during which the car is slowing down. Then I'm going to have another arrow in blue dotted lines, which is going to indicate where the car is stopped. See if you can tell where those are going to be. Remove our dots, as usually we'll just have a curve, and remember to draw your curve smoothly. So there's our red section where the car was slowing down. Then our blue section right there is when the car is stopped. Notice what happens as we're slowing down. We get a curved position versus time graph where the slope of the graph gets less and less steep. That's what happens during the red section. When the object is stopped, the slope will be 0. Okay, let's put it all together in one last example. We'll go crazy. We have a car that starts out from rest and speeds up. Then it starts to slow down, and then it stops for a couple seconds. Then we travel in reverse, speeding up, and then slowing down again and stopping. Okay, all these dots were dropped at equal intervals of time, but every 1 second we dropped one of those droplets. We're going to switch them over onto our, again, position versus time graph, or x versus t graph, and see what kind of weird shape we get. You're going to notice that, first of all, using the dot diagrams is not very easy to see once the motion becomes more complex. But spreading those dots out over time is why we use our position or velocity or acceleration versus time graphs, so we can see the extension of time across the x-axis. This is quite a shape now, isn't it? So remember, we're speeding up, then slowing down, then we're stopped, then speeding up in the opposite direction, slowing down, and stopped. When we have multiple types of motion, you want to break up the motion in the graph into its multiple little components. So here we have the green component of the graph is where we're starting to speed up. And at that inflection point I just pointed to is when we start to slow down. So slowing down is in yellow. Then we have when the car is stopped at the very top of the page in red. Then the car goes into reverse and speeds up rapidly in the opposite direction. So we have a second green portion that's speeding up but in the opposite direction. Then we have another yellow section slowing down very quickly at the very end, and the last red section is going to be our car stopped once again at the very end. Watch the car again, see if you can follow along on the graph. Speeding up, slowing down, stopped. Speeding up in the opposite direction, slowing down, and stopped. Remember, for these graphs where we have multiple types of motion going on, like something traveling for a constant speed, then speeding up, then slowing down, then stopped, you want to separate the graph into those different portions of motion. It makes it a lot easier to analyze and figure out what's going on. You'll also notice in that last graph, you should take a look at it again, rewind and go take a look. You'll notice that when we're speeding up in the positive direction, our slope is getting steeper and steeper. As we slow down, the slope is getting less and less steep. When we're stopped, our slope is 0. So our slope tells us our speed, and if our slope is positive, it tells us we're traveling in the positive direction. Also go back and look at that last graph we did when the car was in reverse, moving back towards its original position. It had a very steep slope, but the slope was negative, indicating it was traveling backwards down the page in the negative direction. Okay, that's all for our motion graphs and dot diagrams for now. Remember, this was all just about the position versus time graphs, and we'll have new videos about different types of graphs we're using. Be sure to practice these understandings in your interactives and concept builders and online problems that are linked to in our class notebook.